Imagine a con artist knocks on your front door.
Okay.
He presents himself as a specialized jeweler, and he offers to clean your dull, tarnished gold bangles. So you hand them over.
As you do.
Right. And he drops them into this beaker of clear, fuming liquid. Just a moment later, he pulls them out, and they are sparkling. I mean, absolutely pristine.
Oh, wow.
Yeah. He smiles, hands them back, and just walks away. But what you don't realize until much later is that your bracelets feel just like a little bit lighter.
Oh, man.
He just stole a significant percentage of your gold in broad daylight without ever leaving with the bracelets.
It's basically the perfect crime.
Yeah.
Executed entirely through invisible chemical warfare. That clear liquid dissolved the gold right off the surface, just trapping the precious metal in the water for him to extract later.
It's wild. And today, we are looking at that invisible warfare happening all around you.
Welcome to today's deep dive. Our mission today is to unpack the fundamental building blocks of our entire physical world, metals and non-metals.
Big ones. Exactly. Whether you are, just brushing up on your chemistry or you just want to understand the fabric of the reality you interact with every single day, this deep dive is going to completely change how you view everyday objects. We're going to look at the salt on your fries, the steel beams in your walls, and the rings on your fingers.
Which is so important because we so often treat the periodic table of elements like this, dusty inventory list.
Right, like a spreadsheet.
Yeah.
Oh.
But these elements are actually a cast of highly dramatic characters. They have wildly different temperaments, intense rivalries, and complex social behaviors that literally dictate how our universe is constructed.
So to understand these characters, I think we have to start by looking at their physical traits. I mean, we categorize these elements by the things we can see and feel. It's almost like sorting music genres.
How do you mean?
Well, you hear heavy guitars, you call it rock. You see something shiny and hard, you call it a metal.
That's a great analogy. The classical grouping rules are entirely based on those sensory inputs. Pure metals are generally lustrous, meaning they shine.
Okay.
And they are sonorous, meaning they ring like a bell when struck.
Yeah.
That acoustic property is actually why traditional school bells or church bells are cast from bronze or brass.
Right, you'd never carve a bell from wood or stone.
Exactly, it just wouldn't work.
They also bend to our will. Right. Metals are malleable, so we can beat them into incredibly thin sheets. And they're ductile, meaning we can draw them out into wires.
Yeah, the ductility is key.
I actually found an unbelievably visceral stat on this. Gold is the most ductile metal on the planet. If you take a single gram of gold, so roughly the weight of a small paperclip, you can stretch that tiny nugget into a wire 2 kilometers long.
Wait, 2 kilometers from a gram?
2 kilometers just from a gram.
That's insane. But the mechanics behind that are fascinating.
Yeah.
Metals are structured in these highly organized crystalline lattices.
Okay.
But because of the way their atomic bonds work, entire planes of atoms can actually slide past one another without snapping the bonds that hold the whole structure together.
Oh, so they stretch rather than shatter.
Exactly. Non-metals do the exact opposite. They're usually just dull solids or invisible gases. And if you hit a solid non-metal with a hammer, it just crumbles.
But the moment you start trusting these physical labels, the elements they start breaking the rules.
Oh, big time.
We think of metals as heavy, rigid things holding up bridges, but mercury is a metal, and it just sits around as a sloshing liquid at room temperature.
Yeah, the classic exception.
And then you have gallium and cesium. These are technically metals, but their melting points are so incredibly low that if you drop a solid piece of gallium into the palm of your hand,
it melts, right?
Your sheer body heat will literally melt it into a silver puddle.
It's wild. The whole illusion of the impenetrable metal just completely falls apart, and the alkali metals push this even further.
Oh, right.
If you take a chunk of pure lithium or sodium or potassium,
you don't need industrial tools to manipulate it. You can slice right through these solid metals with a dull butter knife.
With a butter knife. And the non-metals are out there pulling the exact same tricks. Carbon is a non-metal, right?
Right.
In one architectural setup, what chemists call an allotrope, which is really just a different physical arrangement of the exact same atoms, carbon is graphite, the soft stuff inside a pencil.
Super brittle.
Right. But you arrange those exact same carbon atoms slightly differently and you get a diamond.
The hardest natural substance known to man.
Exactly. With the melting point so high, it defies the whole crumbly non-metal stereotype entirely. Oh, and iodine.
What about it?
It's a non-metal that actually has a shiny metallic luster. It totally looks the part of a metal.
See, because of these visual tricksters, we quickly realized that categorizing elements by their physical appearance is just a trap. The physical labels are super fragile.
So you can't judge a book by its cover.
You really can't.
Yeah.
To truly understand what makes a metal and a non-metal, we have to push past the surface. We have to provoke them and see how they retaliate.
We have to test their chemical personalities.
Yeah.
I like that. If the physical appearance is how they dress, their chemical reactivity is how they handle conflict.
You expose them to water, to oxygen, to acids, and you basically just see who stays calm and who throws a punch.
And chemists track these personalities using something called a reactivity series. It is a strict hierarchy of aggression.
Okay, who's at the top?
At the very top, you have the wildly explosive elements. Sodium and potassium are prime examples here. If you expose pure sodium to something as harmless as cold water.
Or even just the moisture in the air, right?
Yeah, exactly. It reacts so violently that it produces hydrogen gas and enough heat to instantly ignite that gas.
It literally throws a fiery tantrum. You actually have to store sodium completely submerged in kerosene oil just to act as a physical barricade against the ambient air in the room.
You do. But as you move down this hierarchy, the reactions become a little less dramatic. Take calcium, for example.
Okay.
Calcium will react with water, but instead of exploding, the hydrogen gas bubbles just cling to the surface of the metal, making it float.
Oh, that's kind of cool.
Yeah. Then go a bit further down to the middle children of the series, iron, zinc, aluminum. They completely ignore cold water. They won't even react with boiling water.
Wait, really? Boiling water does nothing.
Nothing. You have to blast them with high-temperature steam just to force a reaction.
It's crazy how this hierarchy dictates so much of the world around us. I mean, it's the exact reason your car gets rusty. Iron sits high enough on the list to react with the environment.
Right.
But a gold ring pulled from a shipwreck after, 300 years, it looks pristine.
Because gold sits at the absolute bottom of the social hierarchy. It is utterly stubborn. It flat out refuses to react with oxygen, water, or normal acids.
Which brings us right back to our con artist from the beginning of the deep dive.
Yes, the goldsmith scam. The con artist relies on the fact that gold is almost invincible, which makes people trust that nothing can dissolve it.
But chemists discovered a loophole.
They did, aqua regia.
Latin for royal water. It's this fuming, highly corrosive, freshly mixed solution of concentrated hydrochloric acid and concentrated nitric acid, mixed in a 3-to-1 ratio.
And the craziest part,
What?
neither of those acids can dissolve gold by themselves.
Wow.
Yeah, you could drop gold in hydrochloric acid, nothing happens.
Yeah.
Drop it in nitric acid, nothing happens. But mix them together.
They form a chemical tag team.
Exactly. The mechanism here relies on two separate attacks happening simultaneously. The nitric acid acts as an oxidizer, breaking loose just a tiny microscopic fraction of gold ions.
Okay, and normally it would stop there.
Normally, the reaction would stop right there. But the hydrochloric acid steps in. It provides chloride ions that immediately grab those free gold ions and lock them away into a new compound called chlororic acid.
Oh, so the hydrochloric acid basically sweeps away the evidence?
Yes.
Which forces the nitric acid to break off a little bit more gold, and then the cycle just continues until the solid gold literally vanishes into the liquid.
It's a brilliant manipulation of chemical constraints. But this dissolving of metals, or even just iron rusting in the rain, is driven by a much broader concept called displacement.
Displacement. Okay, how does that work?
Well, the hierarchy of the reactivity series is essentially a list of who can push who around. A highly reactive metal will actually kick out a less reactive metal from its chemical bonds.
So if zinc is more reactive than copper...
And you introduce zinc to a copper compound, the zinc will forcefully evict the copper and take its place.
Wow, so it's a microscopic turf war.
It really is.
But why is there a turf war in the first place? I mean, what makes sodium so insanely aggressive while gold is totally content just doing nothing?
To understand the motivation behind all this aggression, we have to zoom all the way down to the fundamental architecture of the atom itself.
Okay, zooming in.
We are looking at a desperate, universal quest to build a perfect outer shell.
The valence shell, right? The outermost orbit of electrons buzzing around the nucleus of the atom.
Correct. The valence shell is the only part of the atom that interacts with the outside world. Now, there is an elite group of elements called the noble gases: helium, neon, argon.
Right, the snobs of the periodic table.
Pretty much. They are chemically inert. They simply do not react with anything. They don't burn, they don't rust, they don't bond.
Because their valence shells are completely full. They've reached, atomic nirvana. They don't need anything from anyone else.
Exactly. But every other element in the universe is fundamentally unstable and trying to mimic those noble gases.
Mm.
They want that perfectly full outer shell, and they will swap, steal, or share electrons to get it.
Okay.
This is the defining difference between our two groups. Metals are elements that have a few extra electrons in their outer shell. To reach perfection, they need to dump those extra electrons.
Ah, okay.
When they throw away negatively charged electrons, the metal atom becomes positively charged. We call this a cation.
And the nonmetals are sitting on the totally opposite side of the equation. They're just a few electrons short of a full shell, so they are desperately hunting for extra electrons to absorb.
Yes.
And when they grab those electrons, they become negatively charged. In any
Which creates a perfect symbiotic relationship.
I picture it like a cosmic garage sale.
Oh, I like that.
Yeah, let's look at sodium. Sodium is a metal with exactly one annoying extra electron in its outer shell. It is desperate to get rid of it. It's like having an ugly lamp taking up space in your garage. You just want it gone so your space is perfectly clean.
Right.
Then a nonmetal like chlorine walks by. Chlorine has 7 electrons in its outer shell, but it needs 8 to be full. So chlorine is literally wandering the universe hunting for exactly one ugly lamp to complete its living room.
So they strike a deal. The sodium atom gives its electron to the chlorine atom. Suddenly, sodium has a stable, perfect outer shell.
And chlorine also has a stable, perfect outer shell.
Exactly. But by transferring that electron, sodium became positively charged and chlorine became negatively charged.
And opposite charges attract. They snap together like powerful magnets to form a completely new substance, an ionic compound. Sodium chloride.
Which is the chemical name for the table salt you put on your food.
It's so crazy to think about. A violent, explosive metal and a toxic green, non-metal gas swap an electron and become a perfectly safe, delicious crystal.
Chemistry is magic.
Mm-hmm.
But the properties of this salt crystal are entirely dictated by those magnetic attractions.
Right. The positive and negative ions are held together by incredibly strong electrostatic forces.
Very strong. They arrange themselves into a rigid, alternating 3D grid called a crystal lattice. Because these bonds are so tight, ionic compounds are always solid at room temperature.
And they're brittle, right?
Very brittle.
Mm.
If you hit a salt crystal with a hammer, it shifts the lattice, pushes 2 positive charges next to each other, and they repel, shattering the crystal.
It also takes a massive amount of heat to melt them, doesn't it?
Oh yeah, because you have to pump in enough energy to physically rip those magnetic bonds apart.
You know, this actually clears up a huge question I had about electricity.
What's that?
Well, we're told that salt is made of these highly charged electrical ions. But a solid block of salt is an insulator. It doesn't conduct electricity at all.
True.
Yet, if you take that exact same salt and dissolve it in a glass of water, it suddenly becomes a fantastic conductor. Why is that?
It all comes down to mobility. For an electrical current to flow, charged particles must be able to move.
Okay.
In a solid block of salt, those charged sodium and chloride ions are trapped in that rigid lattice. They're locked down. But when you drop salt in water, the water molecules physically wedge themselves between the ions, pulling the lattice apart.
The ions are freed.
They're completely liberated, just floating around in the water. Now, if you apply an electrical voltage, those free-floating ions can easily carry the charge from one side of the glass to the other.
Wow.
Actually, this exact mechanism of dissolved, free-floating ions carrying electrical signals is how the electrolytes in your body tell your heart to beat.
That is mind-blowing. So because metals are so highly motivated to dump their electrons, they are almost never found pure in nature, right?
Almost never.
The Earth isn't just handing us pure blocks of iron or aluminum. They've already reacted. They're already bonded to nonmetals, particularly oxygen-forming rocks.
Which leads us to one of the most significant chapters in human history, really. Metallurgy.
The art of ripping metals away from the elements they are perfectly happy being bonded to.
Exactly. When we dig metal out of the ground, it's trapped in a mineral compound called an ore, and it's surrounded by dirt, sand, and rock, which chemists refer to as gangue.
Gang. What a great word. So to get the pure metal, you first have to wash away the gangue, and then you have to break those strong chemical bonds.
Right. And the weapon you choose to break the bond depends entirely on where the metal sits on that reactivity series we talked about earlier.
Let's start with the easy ones at the bottom.
Low reactivity metals, like mercury. Mercury is often found bonded to sulfur in an ore called cinnabar.
Okay.
Because mercury is relatively unreactive, its hold on the sulfur is pretty weak. You simply roast a cinnabar in the air.
Just heat it up.
Yep. The heat provides enough energy for oxygen to come in, bond with the sulfur, and float away as sulfur dioxide gas. Apply a little more heat, and the remaining oxygen lets go, leaving behind pure liquid mercury.
That seems too easy. But what about the metals in the middle of the hierarchy? Things like zinc, iron, and lead. They hold on to their partners with a much tighter grip.
Yeah, these middle-tier metals are usually pulled from the earth as either sulfides or carbonates, and our first goal is to convert them both into oxides.
Because oxygen is easier to strip away later.
Exactly. But the methods to get there are completely different. If you have a sulfide ore, you use a process called roasting. You heat the ore intensely in the presence of excess air.
Why the excess air?
Well, a sulfide ore is just metal and sulfur. You need to blast it with oxygen from the air so the sulfur has something to bond with and escape as a gas.
Makes sense. What about carbonates?
On the other hand, if you have a carbonate ore, it already contains oxygen. It's bonded to carbon and oxygen. For carbonates, we use calcination. We heat it intensely in limited air. The heat causes the carbonate to break down, releasing carbon dioxide gas, leaving the metal oxide behind.
So you roast sulfides to add oxygen, and you calcine carbonates to bake off the carbon dioxide.
You got it.
Either way, you are left with a metal bonded to oxygen. Now you have to steal the oxygen.
Right, so we introduce a reducing agent. Usually this is carbon. We heat the zinc oxide with carbon.
And carbon is aggressive.
Carbon is incredibly aggressive when it comes to oxygen. It acts as an atomic thief, just ripping the oxygen away from the zinc to form carbon monoxide gas, leaving pure metallic zinc behind.
But carbon is not an omnipotent thief, right? When we reach the very top of the reactivity series, the explosive metals like sodium, calcium, or aluminum carbon is totally useless.
Completely useless.
You can mix aluminum oxide with carbon and heat it all day, and the aluminum flat out refuses to let go of the oxygen. The bond is just too strong for chemical theft.
So we have to abandon chemistry and use brute force physics. We use electrolytic reduction.
Sounds intense.
Oh, it is. We heat the ore until it melts into a liquid, freeing the ions, and then we blast a massive electrical current through it. The electricity physically forces the aluminum ions to one side of the tank and the oxygen to the other.
Wow.
It is an incredibly energy-intensive process, which is actually why aluminum used to be considered more precious than gold.
I remember reading that. Napoleon used to serve his most honored guests on aluminum plates.
Yeah, because it was so hard to extract.
And even after all that, we still run the metal through electrolytic refining, using electricity to dissolve the impure metal and rebuild it atom by atom on a pure plate, letting all the residual gangue drop to the bottom as an anode mud.
It's a huge effort.
But there are moments where we can use these intense chemical bonds to our advantage, right? Instead of just fighting the reactivity series, we can weaponize it.
Oh, yeah. The thermite reaction is the perfect example of this.
I love this one. Think about how hard it is to melt iron. Now imagine doing it in a few seconds, out in the middle of a remote forest, using nothing but aluminum powder and rust.
It sounds like sci-fi.
It really does. If you mix iron oxide, which is rust, with pure aluminum powder, the aluminum, sitting higher on the reactivity series, forcefully displaces the iron.
Right, because it's more aggressive.
Exactly. It violently rips the oxygen away from the iron. And this reaction releases just an apocalyptic amount of heat. It gets so hot so fast that the iron left behind is instantly melted into a glowing liquid state.
And engineers use this localized volcano to weld cracked railway tracks together right in the field.
It is a stunning display of thermodynamics, but it also highlights a kind of depressing reality. We spend massive amounts of energy and electricity to purify these metals, but nature abhors pure metals.
It really does. The moment we pull them from the furnace, the environment begins attacking them, trying to bond with them and return them to the stable ores we just dug out of the ground.
The endless war of corrosion, we see it everywhere. Silver reacts with trace amounts of sulfur in the air, turning black with tarnish. Copper reacts with moist carbon dioxide in the atmosphere to form a green coat of copper carbonate, which, by the way, is the exact reason the Statue of Liberty is green.
Fun fact. And then there's iron rusting.
Rust is the worst.
It is. But rusting is a highly specific chemical attack. Iron actually requires a tag team of both oxygen and liquid water to form rust.
It needs both.
It needs both.
Yeah.
If you seal an iron nail in a tube of boiled water with oil on top to block the air, it won't rust. If you put it in a tube of dry air with a desiccant to absorb all moisture, it won't rust.
To fight this, we paint our bridges, we oil our car parts, but the most ingenious defense has to be galvanization. Coating iron or steel in a thin layer of zinc.
Yeah, and what's crazy here is that zinc is actually more reactive than iron.
Wait, really? Then why use it as a shield?
That is precisely the point. It's a sacrificial layer. If a galvanized pipe gets scratched and the iron is exposed to the air, the oxygen will attack the metal. But because the zinc is more reactive, it will essentially throw itself in front of the iron, reacting with the oxygen first. The zinc sacrifices itself to maintain the structural integrity of the iron beneath it.
Like a bodyguard taking a bullet. That is so cool. But eventually, paint chips and sacrificial layers are eaten away. If you want to permanently beat nature, you have to change the metal itself. You have to cheat.
You mix the metal with other elements to create an alloy.
Right.
Alloying fundamentally alters the physical properties of the material. Pure iron, for instance, is actually quite soft. If it gets hot, it stretches. You cannot build a skyscraper out of pure iron.
It would just bend.
Exactly.
Yeah.
But if you melt it down and mix in a microscopic amount of carbon, just 0.05%, it becomes hard and strong.
Because earlier we talked about how pure metals are organized in neat grids, allowing layers of atoms to slide past each other.
Yes, the sliding planes.
But if you jam a bunch of different sized carbon atoms into that grid, it's like throwing gravel into the gears. The layers can't slide anymore, the metal becomes rigid.
Exactly. Add nickel and chromium to that iron, and you get stainless steel, which completely refuses to rust. We mix copper and zinc to get brass.
Bronze is copper and tin, right?
Yep. We mix lead and tin to make solder, which artificially lowers the melting point so we can safely fuse electrical wires together without melting the components.
Even the gold jewelry we wear isn't pure. 24-karat gold is 100% pure, but it is so soft you could literally bend a ring with your bare hands.
It would get destroyed by everyday life.
So jewelers use 22-karat gold, an alloy of 22 parts gold mixed with 2 parts silver or copper. Those strategic impurities give it the strength to survive.
Which brings us to perhaps the greatest metallurgical mystery on the planet.
Oh, the Iron Pillar in Delhi. This is the ultimate historical flex.
It really is.
It is a massive iron monument, 8 meters high, weighing 6 tons, constructed over 1,600 years ago. It has stood through a millennium and a half of Indian monsoons, blistering heat and humidity, and it hasn't rusted.
It's baffling. But ancient Indian metallurgists developed an extraction and alloying process that created a protective film of complex phosphates over the iron, permanently shielding it from the atmosphere.
Wow.
It's a testament to the idea that the purity of a metal is often its greatest weakness. By introducing the right impurities, we perfect the material for our world.
What an incredible journey we've been on today. I mean, we started by looking at the deceivingly shiny surface of metals. We uncovered their explosive chemical tempers driven by a cosmic garage sale of electron swapping.
Yeah, that was a fun visual.
We watched humanity use massive heat and electricity to rip these elements from the earth. And finally, how we deliberately contaminate them with impurities just to outsmart nature's constant attempts to rust them back into dust.
It really forces you to look at the engineered world differently. Every suspension bridge, every copper wire, every pinch of table salt is a frozen moment in an ongoing atomic negotiation.
It really is. And, it leaves me with one final thought for you to carry with you. We talked about the noble gases earlier.
The snobs.
Right, the snobs. They are perfectly pure, their atomic shells are completely full, they have achieved absolute stability, and because of that perfection, they do absolutely nothing. They are invisible, inert, and entirely uninvolved.
It is only the elements that are missing something that actually act.
Precisely. All the dynamic, explosive, world-building chemical reactions we just explored, the reactions that forge mountains, power technology, and make biological life possible, are driven entirely by microscopic imperfection.
That's deep.
It is the atomic desire to be fulfilled that drives the entire system. It makes you wonder, is imperfection actually the true engine of the universe?
It definitely forces us to rethink what it means to be complete.
The perfect, stable things just float away. The real magic, the real structure of our world happens when things are beautifully, aggressively imperfect. Thanks for joining us on this deep dive. Until next time.